Hello friends, here we are going to start a new topic, that is direct and bending stresses. In the direct and bending stresses, we have two important points. First one is the core of section and another one is chimney subjected to wind pressure. See, the first concept, that is actually loaded column. The load which is coincide with the centroidal axis of the column is called as actually loaded column. You can see here, this one is point. On that point, the load P is acting. You can see this is the intersecting point of the both axis, first axis, and this one is the second axis. And P is acting on this point. The load which is coincide with the centroidal axis. This is the centroidal axis. You can say what in by. You can see what in by centric loading. The load whose line of action does not coincide with the axis of column is called as an eccentric load. Due to eccentric load, both direct stress and bending stresses are induced. So combined maximum stress is equal to direct stress plus or minus bending stress. It's nothing but combined maximum stress is equal to direct stress, that is sigma naught plus or minus sigma b. Direct stress is equal to P upon subjected cross-sectional area. And bending stress is nothing but M upon Z. So maximum stress, sigma max, is equal to P by A plus M by Z. Maximum stress, that is compressive. The minimum stress, you can see sigma min is equal to P by A minus M by Z, tensile. So you can see this diagram. Diagram A, B, C, and D. Here you can see the load is acting here. This is the eccentricity E. Here you can see the B diagram. This is the eccentricity. P is acting here from top. You can see this P is equal to P is at center. You can see plus moment, that is P into E. Condition for stress distribution at the base. If direct stress is greater than sigma B, the stress throughout the section will be of same nature, that is compressive. If sigma is equal to direct stress is equal to bending stress, the stress throughout the section will be same nature, it is compressive. In this case, sigma max is equal to 2 into sigma naught and sigma mean is equal to 0. We'll show you in the diagram. And third case, that is sigma naught is less than sigma b, means direct stress is less than bending stress. The stress will be partially tensile and partly tensile and partly compression. You can see here P is here. This is the eccentricity, sigma mean. This one is the sigma max. In this diagram, sigma naught is greater than sigma b. In this diagram, sigma naught is equal to sigma b. You can see sigma mean is equal to 0. Sigma max is equal to 2 into sigma naught. Here, if sigma naught is less than sigma b, then sigma mean, you can see here, this is the sigma max, and this one is sigma mean. If direct stress is less than sigma b. 4 conditions are very important. First one is just cross section of column. This one is first case. In the first case, sigma naught is greater than sigma b. The second case, sigma naught is equal to sigma b. This one is sigma naught is less than sigma b. Eccentricity. It is the horizontal distance between the line of action of force and the centroidal axis, it is denoted by small e. It produces bending stresses in the member. See different stress distribution for different sections. For a rectangular section, we know that direct stress is equal to P by A. Another important topic, that is core of section. It is a section within which no tension will be produced when the axial load is applied. That is called as core section. There is one important rule, that is middle third rule for rectangular section. For no tension, we know that E is equal to Z by A. So you can see this is Ex, this one is Ey. That is d by 3, d by 3, d by 3. You can see this distance is base, this distance is depth. So b by 3, b by 3, and this one is b by 3. So E is equal to Z by A. So the area is equal to B into D. We know that sectional modulus is equal to Ixx upon y bar. Zyy is equal to Iyy upon x bar. So BD cube by 12 and y bar is d by 2. So BD square by 6 is the formula for Zxx, and Zyy is equal to BD square by 6. So Ex is less than or equal to Zxx upon A, and Ey is equal to Zyy upon A. So Zxx is nothing but BD square by 6, and area is nothing but B by D. So E is less than or equal to D by 6. Here you can see E is less than or equal to dB square by 6, that is BD. So here E is less than or equal to B by 6. So 2E is less than or equal to D by 3. Here 2 is less than or equal to B by 3. For no tension condition, the load must lies within the middle third shaded area of eccentricity 2E as shown in figure. Central shaded portion is known as core or kernel of section. You can see here. This is the middle third rule. So very, very important. And see here. The distance is d by 3. This distance is d by 3. So middle quarter rule for circular section. Again, Z is equal to Ix upon y bar. So E is equal to pi by 4 into d square. It is the formula for area. So Z is equal to pi by 64 into d raised to 4 by d by 2. So pi d cube by 32 is the Z for sectional modulus. This is the area. For no tension condition, we know that E is equal to Z by A. We have value of Z, we have the value of A. So E is less than or equal to D by 8. So 2E is less than or equal to D by 4. Therefore, for no tension developed in the section, the load should be applied within 1/4 diameter of circle as shown by shaded area. You can see here. Similarly, for a different section, you can calculate eccentricity for hollow circular shape. So the next topic, that is stresses at base. The formula, column subjected to eccentric load about one axis only. Formula is stress is equal to direct stress plus or minus bending stress. So stress is equal to P by A plus or minus M by Z. Here I am explaining only one problem to you. Can understand how the stress distribution diagram we can draw for a direct and bending stress. Every time they are asking one question related to the eccentricity. It's very simple by using only one formula. Symmetrical column with eccentric load about one or two axes. Here we have one problem. You can see here a rectangular pier is subjected to compressive load of 450 kilonewton as shown in figure. Find the stress intensity at four corners of the piers. This problem is from December 11 for 10 marks. You can see A, B, C, and D is given. Base is 1500. If depth is also given, that is 1000 mm. You can see this diagram. 250 from this dotted line and 250 from this dotted line. So base is given, that is 1500 mm, is 1.5 meter. Depth is 1000 mm, that is 1 meter. So EXX is equal to EYY is equal to E, that is 0.25 meter, and the W is 450 kilonewton is given. To find stress at A, stress at B, stress at C, and stress at D. So we know that. See, this is a very important problem. Here I am just explaining the steps. First of all, you have to calculate area, that is by using formula B into D, you will get area, that is 1.5 meter square. We know that direct stress is equal to sigma naught is equal to W by A. We have the value of W, we have the value of area. You will get answer 450 divided by 1.5, 300 kilonewton per meter square. So the bending moment about x axis, it is mx. X is equal to myy. Here is equal to P into E. So 450 into E, that is 0.25, is equal to 112.5 kilonewton into meter. Now see the sectional modulus. We have formula BD square by 6 for rectangular section. For ZYY, formula is DB square by 6. So the sectional modulus ZXX is equal to 0.25 meter cube. ZYY is equal to 0.375 meter cube. After getting the value of MXX, MYY, then ZXX and ZYY, you can calculate bending stress. It is MXX upon ZXX. You will get bending stress at XX. So the value of bending stress, that is 450 kilonewton per meter square. Sigma YY is equal to MYY upon ZYY. You will get answer 300 kilonewton per meter square. Now see stresses at each and every corner. Formula stress, total stress is equal to direct stress plus bending stress about XX plus or minus bending stress about YY. So here we have 4 points A, B, C, and D. You have to consider direct stress, bending stress at XX, and bending stress at YY. First of all, you have to write for A, B, C, and D. First of all, write direct stresses, sigma naught, sigma naught, sigma naught, sigma naught. Here, similarly for sigma BXX, sigma BXX, sigma BXX, this one is sigma BXX. Again, for YY, you have to take sigma BYY for A, sigma BYY for B, sigma BYY for C, sigma BYY for D. And after that, you can write sign conventions. See, come at here. Here you can see point is acting at first quadrant, A and B. See A and B point. While considering XX, you can see both signs are minus for XX, because above the dotted line, above this axis, first corner is there. So while considering XX, A and B will be minus and C and D will be plus. See, again I'm explaining you. Point is acting in the first quadrant. So above this dotted line, above the horizontal axis, the effect of that load will be here. So above this horizontal line, means at point C and D, the signs will be positive, and below this signs are negative. You can see here. While considering YY, you can see here, this is the vertical axis. Now here you can see right side of the vertical line, the points are C and B. So C point and B point, that is positive, because effect will be at this side only. At this side, D and A will be negative sign. So see, D and A will be negative. Now we have the value of direct stress, bending stress at XX, bending stress at YY. Accordingly, you can put the values and you can find out stresses at each and every column. See the value minus 450, 150, 1050 kilonewton per meter square and 450 kilonewton per meter square. After getting all the values, you can draw the diagram A, B, C, D. We have all the values for A, B, C, and D. Just by taking the values, you can draw this stress distribution diagram. You can see here. This is a stress distribution diagram. At A, we have value that is minus 450. At B, plus 150. So distribution diagram will be like that. At B, distance is 150, at stress is 150, and at C, distance is 1050. Both values are positive, so stress distribution diagram will be like that. At C, distance is 1050. At D, it's a plus 450, so distance will be like that. But at AD, at A minus, so we have taken minus, but at D, the distance is positive, that is 450 kilonewton per meter square. According to scale, you have to take the distance. You will get this type of distribution diagram. See, by using simple formula, first of all to calculate area, then direct stress, then bending moment about XX, then bending moment about YY, then sectional modulus. After getting sectional modulus, you have to calculate bending stress. After getting bending stress, you can calculate stresses at each and every column. I have explained you the simple trick how to take sign. In the next video, we will see the another topic. Thank you very much.